Yes, please start.
Okay, ma'am. Hope it is visible.
Yes, you are.
Okay. Good morning, everyone. Thank you so much for joining KS School of Business Management in association with the Department of Mathematics, Gujarat University. Welcomes you all on the ninth day of the UG level Fundamentals of Mathematics 2020 workshop. Our today's speaker is Ms. Karisma Kerawal. She is pursuing her PhD from the Department of Mathematics, Gujarat University. She has published 10 research papers in various national and international journals. Presently, she is working as an assistant professor at Silver Oak University. And today, she is going to deliver a lecture on very interesting topic, graph theory. So now I, Keru Thakkar, invite Ms. Karisma Kerawal to deliver a lecture on graph theory. Over to you, ma'am.
Thank you so much, Keyur sir. I'm just sharing my screen. I hope I'm audible very clearly.
Yes, madam.
Yes, ma'am.
Okay, thank you. So, yes, everyone, I
Yeah,
try
it is
KS School
visible. It is visible. Please go ahead.
of Business Management. Okay, yes, ma'am. So, thank you so much, KS School of Business Management and Department of Mathematics, Gujarat University, for giving me this opportunity to share my knowledge with all the people. Today's our topic is graph theory, and how do we start this graph theory? We will first explore the origin of graph theory, as how this graph theory came into. What were the people thinking over there? So, the very origin of graph theory is the Koenigsberg bridge problem. The first paper in history of graph theory on the seven bridges of Koenigsberg in Persia, which is now called as Russia. So, what exactly was this Koenigsberg problem? It was a problem that we have to find a walk by crossing each and every bridge once and only once. Every bridge must have been crossed, and all the bridges should be crossed completely. So, this was the problem which rose a question that can there be such walk that we can completely cross all the bridges? So, Euler in 1736 gave topics. We will need some basic definitions and terminologies. For that, we'll start with the very first definition, a graph. Graph capital G is a set V of G, comma E of G consists of two finite sets, a non-empty vertex set V of G, and in E of G is assigned an ordered pair UV in V called n vertices of V. A loop in a graph capital G is H whose both end vertices are same. Two or more edges are parallel edges if it has no loop and no parallel edges. The next definition is of degree of vertex V. In G, it is total number of edges incident on the vertex, counting each loop twice. If there is a loop, we have to count that loop twice. Or if it is a simple edge, then we just count it once. It is denoted by D of V. The vertex whose degree is 1 is called pendant vertex. And the initial edge, sorry, the vertex whose degree is 1 is called pendant vertex and the incident edge is called pendant edge. The graph with no edge is called a null graph. Let us see and understand this with an example. So we have taken one graph, and what data can we abstract out of this graph? The very first thing which we can see is a set of vertices. So I have mentioned V of G as V1, V2, V3 up till V7. This all are the vertices present over here. In the graph you can see the dots which are present are the set of vertices. Edges E1, E2, E3 up till E8. All are the edges which you can see they are already named over there. V7 is an isolated vertex. You see on the left top corner in the figure there is V7 and which has no edge incident on it. So it is an isolated vertex. V4 is a pendant vertex. E4 is called a pendant edge. E7 is a loop. And E1, E2 are the parallel edges. From the same figure, we can also find degree of vertices. The degree of vertices, I have mentioned degree of V1 is equal to 3. You can see on V1 there are 3 edges. So degree is 3. Degree of V3 is 3. V4 is 1. V6 is 4. V7 is 0 and so on. We can calculate the degree of all the vertices. The next step, the grafting, if there is between the edge set E1 and E2 in such a way that if there is an edge even in the vertices with end vertices U1 and V1 in G1 has the end points as U2 and V2 in G2. A pair of graph is called graph isomorphism. I'm sorry, am I connected over again? Okay, thank you, sir. So sorry for the interruption. I was explaining the isomorphism of graph. We have two graphs G and G dash. Now we want to check whether they are isomorphic to each other or not. How do we check it? See, first thing we will count number of vertices, whether they are same in both the graphs or not. In G we have 5 vertices and in G dash also we have 5 vertices. The next step is we will check the edges whether they are same in number or not. So in G there are 5 edges as well as G dash there are 5 edges. So two conditions are satisfied. The last thing is we have to check whether the edge in G which correspond to the end vertices are same in G dash or not. For example, I take an edge AB in G. It corresponds to the edge A dash B dash in G dash. So similarly, we can find all the edges which corresponds to G dash. So yes, it admits as well as endpoints of each corresponding are same. The next example is graph isomorphism. Here it is not an graph isomorphism because you can clearly see that edge between B and E in graph G is not there in G dash, or you can say so the same thing is written over here. At the edge in between the cycle, they do not correspond with each other, and so this two graph G and G dash are not isomorphic to each other. The next and very important, for any graph G with n vertices, say v1, v from 1 to n, d of vi is equal to 2e. Expanding this equation in words, I would like to say sum of degree of all the vertices is equal to 2 times the number of edges. This is a one-line proof, and so it has two endpoints. If we are counting the degree, we will count one edge 2 times because it has two endpoints. So hence that is written in the proof that when degree of vertices are summed up, each edge is counted twice, and hence now we should verify the fundamental theorem of graph theory. Here I have taken the same example which we used before. As we know, there are 7 vertices and 8 edges. For all the 7 vertices, I have mentioned the degrees. Degree of v1 is equal to 2, v6 is 4, and v7 is 0. We just sum it up because the fundamental theorem says that we have to sum all the degree of vertices, and it gives us degree of vi is equal to 16 is equal to 2 into 8 is equal to 2e, because 8 is the total number of edges in our graph. The total number of edges are 8. Hence, the fundamental theorem of graph theory is verified. Now, simple graph in which pair of distinct vertices is joined by an edge, or we can say this definition as a complete graph Kn is a simple graph with n vertices such that degree of each vertex is n minus 1. So this both the ways we can explain a complete graph. So what basically is this complete graph? On the right I have a figure of complete graph K5. A K-regular graph is a simple graph with vertices of equal degree K. We note that a complete graph is n minus 1 regular graph because each vertex has degree regular graph. The next definition is of bipartite graph. Let G be a graph if the vertex set V of G can be partitioned into two non-empty subsets X and Y with the condition that X union Y is whole set V and its intersection S X intersection Y is null set, such that each edge in G has one end vertex in X and other end vertex in Y. Then G is called a bipartite graph. Here is one of the example. There are two sets X and Y. So I have labeled the vertices on the upper vertices as X1 and X2 and the lower vertices as Y1, Y2, Y3. The next definition is of complete bipartite graph. A complete bipartite graph is a simple bipartite graph with partition set X and Y such now there cannot be a missing of edges from X set to Y set. It is done and n is the number of vertices in Y. Here is the example. Complete bipartite K2, 3, where 2 is the number of vertices in X and 3 is the number of vertices in Y. The next definition is of subgraph. Let H is a graph with vertex set V of H and H set E of H. Similarly, we are taking a graph capital G with vertex set f of G if V of H is subset of V of G and E of H is subset of E of G. Means vertex sets are subset of each and H set is also a subset of G. We can also call it a reverse wise that G is a supergraph of H. I've taken an example. On the left, G is our complete graph K5. From that, a very small part A, C and E, two edges are taken as graph H. So we call supergraph of H. Walking in a graph. A walk in a graph is a finite sequence W as V0, even V1, E2, V2 up till Vk minus minus 1 ek vk, whose terms are alternatively vertices and edges, such that for 1 less than equal to I less than k, the edge ei has n vertices as vi minus 1 and vi. A trail is a walk with all the different edges. A path is a walk with all the different vertices. And when we take different vertices, it automatically becomes that there are different edges also. So into the bracket I have written, and hence the edges. A walk or trail is closed when v0 is equal to vk. A cycle in a walk with different vertices means the end vertex and the initial vertex are same. Let us understand all these definitions with an example. Starting an example, I have taken one graph and there is a question that can you find a walk? Now this question is, we can change this question and there can be many questions like this. Like, can we find a walk from V0 to V8? Or can I find a walk from V1 to V5? Or the question can be, can I find a walk of distance or length 5? Or else can I find a walk such that it covers all the vertices other than V7? So these are many type of questions which come to our mind. But this is the very basic question, and answer to this question is yes, we can have more than one walk. Like I've taken few examples: V0, even, V1, E2, V2, E8, V6, E11, V7, E10, E8. Or I've taken V4, V6, V5, or V2, E3, V2, E5, V4, E6, V5. These are the few walks. Our next question is, can we find a trail out of it? First, we have to keep in mind what is the property of trail. It is that no edge should be repeated. And I have taken once again few examples like V1, E2, V2, E8, V6, E11, V7, E10, V8. The next is V4, V6, V5, V7, V6. Last is V2, E3, V3, E5, V4, E6, V5. I've given few examples. There can be many trails out of it. A closed trail with k edges is called a cycle of length k. The next question is, can we find a path out of it? Now again, the property of path is that no vertices should be repeated. And we have taken 3 examples: V0, even, V1, E2, V2, E8, V6, V3, E5, V4, E6, V5, or V2, E3, V3, E5, V4, E6, V5. These are the few examples of path. A graph G is called connected if we can find a path in between any two of its vertices. So if there is no path between any two vertices, we can say that this graph is disjoint, or we can say that this graph has more than one component. So it is very necessary that we should find a path. There are few results connecting to the path and cycle. So the very first result, given any two vertices U and V of graph G, every UV walk contains a UV path. Every path is a trail, but every trail is not a path. Characterization of bipartite graph using a cycle. Every G be a non-empty graph with at least two vertices, then G is bipartite if and only if it has odd cycles. I would like to highlight this for bipartite graph using cycle. G is bipartite if and only if it has no odd cycles, only even cycles should be allowed. A adjacency matrix representation of a graph. So from a graph, now we are connecting it to the matrices. So let G be a graph with n vertices listed as V1, V2, V3 up till Vn. The adjacency matrix of G with respect to this particular listing of n vertices of G is a n cross n matrix. Means this is a square matrix. It is denoted by A of G is equal to Ai, where Ij entry is Aij and number of edges joining the vertex Vi to the vertex Vj. We will understand this definition using an example. I've taken an example so we can see there are 6 vertices. So for forming a matrix, we have taken 6 rows and 6 columns. Each row is denoting vertex A, B, C, D, E, F, and similarly column also. So how do we construct this matrix? For the very first element, A and A, we are checking where A has a loop. There is no loop, so we put 0 at that place. Now we are checking whether A has any edge incident to B or not. So yes, there is an edge between A and B, and so we have given number 1 there. Similarly, this matrices is formed. The 2 over there is the parallel edges, because you can see in between A and E there are 2 edges. So there is 2 number written in the matrices. So from this matrix, what can we predict? From this matrix, we can predict that or the column sum gives us the degree of particular vertex if all the diagonal entries of 0 are 0. Then we can say that there is no loop present in the graph. If there are no parallel edges, then all the entries are either 0 or 1. If there are no parallel edges, then we will just have either a 0 entry or 1 entry. Moving to the next matrix representation, that is incidence matrices listed with V1, V2, Vn, and T edges listed as E1, E2 up till En. The incidence matrix of G with respect to the particular listing of n vertices and T edges of G is the n cross T matrix. Now this will be a rectangular matrix. Obviously it can be a square matrix, but it can also be a rectangular matrix. It is denoted by Mg, where Mij is the number of times, which is a summarizing of the definition, that is 0 if Vi is not an end of Vj, it is 1. If Vi is the end of a non-loop Vj, means wherever it is loop, we are going to put 2. So taking an example, I've taken the same example, just given the names of the edges. You can see there are 9 edges. So in the column part, we have taken E1 to E9. In the row part, we have taken A to F. And there is a matrix over here. Now, how do we construct this matrix? You can see or you can observe the edge E1. E1 has 2 end vertices, A dash and B dash. And so in that first column, we have 1, 1 entries at A dash and B dash part. Other places we have 0. You can check edge E8, means the second last column. The edge E8 is a loop, and loop at the vertex B. So in the row of vertex B, there is a value 2 over there. So this is the construction of incidence matrix. What are the properties of this incidence matrix? The row sum gives us the degree of the vertex. The column sum is always 2, as each edge will have 2 vertices as the end vertices. 2 columns are same if they are parallel edges and if it is a loop. Then column will have 1 entry as 2. Trees. The next topic is a graph is called acyclic if it contains no cycle. A tree is connected acyclic graph. I've taken an example. Now this example, on the left hand side, we have few numbers 1, 2, 3 up till 6. These numbers are the number of vertices in the tree. Please have a look on number 5. Number 5, we have 3 graphs. This graph actually shows that there are 3 non-isomorphic trees which can be formed using 5 vertices. 3 trees with 7 vertices. So here we have 11 non-isomorphic trees in which 7 vertices are involved. Few results on trees. Let G be a graph without any loop. If for every pair of distinct vertices U and V of G, There is precisely one path from U to V. Then G is a tree. Let T be a tree with at least n vertices and let P as U0, U1 up to UN be the longest path in T. Then both U0 and UN, first and last vertex, has degree 1. Means that is degree of U0 is equal to degree of UN is equal to 1. If T is a tree with n vertices, then it has precisely n minus 1 edges. And the last result is, if G is acyclic graph with n vertices and k components, this time it is not a connected graph, it has k components, then G has n minus k edges. This last two results helps us to find number of edges or vice versa, number of vertices, if we have a graph or we have few data with us. Bridge and its results. What is a bridge? Any edge E of graph capital G is called a bridge or a cut edge if the subgraph G minus E has more connected components than G. Result of a bridge is an edge E of a graph G is a bridge if and only if it is not a part of any cycle in G. G is a tree if and only if every edge of G is a bridge. Means in a tree we have n minus 1 vertices, and if we remove any edge, it will divide the tree into two parts, and so each edge is a bridge. The next topic is spanning tree. A spanning tree of graph G is a spanning subgraph of G that is a tree. So I've taken an example. This example has a triangle, and now of this triangle we have spanning trees as ABC. There is no edge AC. In the second there is no edge CB, and in third there is no edge AB. So these are the three spanning trees out of the graph G. Results on spanning tree. A graph G is connected if and only if it is a spanning tree. Cayley in 1889 used a tree to count number of saturated hydrocarbons containing a given number of carbon atoms. He was the first person to use this term as tree. Then he gave the result that complete graph Kn has n raised to n minus 2 different spanning trees. Just giving one example out of this is taking a graph K3, which we just saw in the previous example. It has 3 raised to 3 minus 2 is equal to 3 different spanning trees. We just saw there were 3 spanning trees. Now methods to find the spanning trees. We have 2 different types of methods, Kruskal's algorithm and Prince algorithm. Before understanding the method, we need a definition: weighted graph. A weighted graph is a graph G in which each edge E has been assigned a real number W of E, which is called weight of E. If H is a subgraph of weighted graph, the weight WH of H is sum of weight WE plus WEQ plus up till WEK, where even E2 up till EK is the set of edges of H. Starting with the Kruskal algorithm, we'll first see the algorithm and then we'll see the example on it. The first step is to choose an edge even in G such that the weight of even is as small as possible and even is not a loop. The step 2 is, if edges even E2 up to EI has been chosen, then we have to choose the next edge EI plus 1, which is not already been chosen, such that there are 2 conditions. The first is induced subgraph H, even E2 up till EI plus 1 is acyclic, means it does not form a cycle, and weight of EI plus 1 is as small as possible with respect to condition 1. The last step is, if G has n vertices, then we stop after selecting n minus 1 edges. And if not, then we again go to step 2 and repeat that step 2. Example of Kruskal algorithm. We have an image, a graph. We have to find a spanning tree out of this. So you can see the minimum weight in this graph is 1. And this 1 is at 2 places. One is AC and another edge is EG. So the step 1, we have to select the edge with lowest weight. I have supposed edge AC. Some of you may think whether we can take EG or not. Yes, we can take EG also. It is up to us. you can take either of the edges. The next step is we have to select another edge with the lowest weight and it should not be a loop, nor it should form a cycle with previous edge. And so we take EG. Because the lowest weight of the remaining edges is again 1, so we have considered AC and EG, both the edges. The next part would be the lowest weight is 2. Now we have 3 options with us: DC, CB and AB. Now we can choose any of one edge out of this, but I have chosen CB. Note that we showed edge AB cannot be selected by me. If you have selected AB, then you cannot select CB because it will form a cycle over there. And second point to be kept in mind is there are 7 vertices, so we have chosen CB. The next step is we have selected CD, CB and FG, 3 edges. So by using or taking these edges, we get the octane spanning tree. You can see this weight is the lowest weight and this is a spanning tree. The next is Prim's algorithm. The Prim's algorithm, first step is to choose any vertex V1 of G. Second step is to choose even such that V1, V2 and V1, V2 are not same, means it should not be a loop. Even step 3, edges even E2 up till EI has been chosen involving the end vertices V1, V2 up till Vi plus 1. We choose the edge EI plus 1 such that its endpoints are Vj, Vk, where Vj belongs to the previously vertices and Vk does not belongs to the previous selected vertices. EI plus 1 should have the smallest weight. Going to the step 4, we stop after we have selected n minus 1 edges. If not, we will again repeat step 3. The example of Prim's algorithm, there is an image. In this image, we have started with vertex A. Once again, your question arises in the mind that can we start with C? Can we start with D? Yes, you can start with any vertex. Or if someone has mentioned you that I want here, there's nothing mentioned, so I'm taking or I'm initializing with vertex A. You can observe that on A, there are 4 edges incident with weight 7, 14, 12 and 10, out of which 7 is the least weight. So we have considered the edge AD. When I have taken edge AD, the end vertex is D and we have to now start from the end vertex D. From D, the incident edges are of weight 13, 6 and 11. The least weight is 6, so we select DC. The end vertex is C and so now we start from C. Checking the vertices incident on C, the weight is 8, 6 and 9, 12. So we take the edge CE. CE, the end vertex is E and similarly we continue to find the next spanning tree. There are 4 edges which have been selected over here. The difference between Kruskal and Prim's algorithm. In Kruskal algorithm, it leads to the several subtrees grown simultaneously and then joined together. While in Prim's, it leads to one subtree growing steadily from one initial vertex. In Kruskal algorithm, it depends on being able to detect a cycle or not. While in Prim's algorithm, we are not choosing the previously chosen vertex, so there cannot be a chance of selecting a cycle. The next method is to find shortest path. The method is breadth first search technique for shortest path. Let G be a graph with 2 vertices S and T which are specified in G. What does this algorithm teach us? For step 1, we label the vertex S with I is equal to 0. Means for the very first step at S, we label it or we initialize it with I is equal to 0. Then find all the unlabeled vertices in G which are adjacent to the vertex labeled with I. If there are no such vertex, then T is not connected to S. If there are such vertex, then label them with I plus 1. Moving in this process, if T is labeled, then go to step 4. But if T is not labeled, then we go to step 2 and we keep request to T is I plus 1 and we stop there. So basically, I would like to explain it in an example. In a graph, we have S and T mentioned in the graph. You can see where S, it is written I is equal to 0, that is initialization. Now we label all the vertices adjacent to S with I is equal to 1. All the edges which are adjacent to I is equal to 1 are now labeled with I is equal to 2. And we continue. During this process, we get this image. You can clearly see that S is initialized with 0. The adjacent vertices are labeled with 1, 2, 3, and the last vertices are labeled with 4. What do we mean? Means this gives us the information that shortest path from S to T to reach is 4. The next is Diksha's algorithm. Step 1. Let phi of S is equal to 0 for all the vertices V is not equal to S. Phi of V is equal to infinity. Rename this vertex of set S V as T. This T is the set of unlabeled vertices. Step 2 gives us, let us U be the vertex in T with the minimum value phi of U. Step 3, if U is equal to T, then stop. If not, then we go to step 4. Step 4 is, for every edge E is equal to UV incident on U. If V belongs to T, then phi of V is greater than phi of U plus weight of E, means weight of the edge. Change the value of phi of V to phi of U plus W of E. This in short means that we have to take the minimum weight out of phi of V or phi of U plus W of E. Change T to T minus U and go to step 2. Let us understand this using an example. So this is our example and we have to find the shortest path from the vertex C. Now again a question will arise, can we start with C, can we start with A? Yes, you can start with any, but here in particular case I am taking the vertex C. So the very first step for this was to select phi of C is equal to 0 and rest all as infinity. So here you can see in the image C as infinity. The next is in step 2 we assign the weight to the adjacent vertices of C with weight of the edge. Like you can see the very first edge CA. It has weight 1 and so A is being given the label phi of A is equal to 1. The edge CB has weight 7 and it has been given the label 7. The edge D is of weight 2 and phi of D is now assigned as 2. Moving to step 3, we have fixed A, that is phi of A is equal to 1. Why? Because 1 is the minimum weight. There can be no weight less than 1. Now we have to select for B. You can clearly see there are two ways to reach B. One is directly from C to B with weight 7 and another is by traveling a long distance C to A and A to B. But total of this is 4, which is obviously 4, and so this 7 has been striked out and 4 has been replaced. So now similarly 4 is being fixed and D is also fixed. For the vertex E, now again we have two paths. We can travel from C to D and D to E. We can also travel from C to B and B to E. While traveling from C to D and D to E, we get weight as 9. And from traveling from C to B and B to E, we get minimum weight as 5. So 5 is the minimum and so we freeze. So finally, using this method of Diksha's, we are getting the shortest path between C and A as 1, between C and B as of weight 4, From C to C, traveling we get 0. From 5. This was all about finding the shortest path. Now coming to the Eulerian graph, a trail in G is called a Euler trail if it includes every edge of G. A Euler cycle of G is a closed walk of G which includes every screen. We have to check whether it is Euler or not. On the left hand side, the graph, it is a Eulerian graph because we can find a cycle in which we can cover all the edges. But on right, we cannot cover all the edges. We have to repeat some. So it is not an Eulerian graph. Few results on Eulerian graph. Let G be a graph in which the degree of every vertex is at least 2, then G contains a cycle. A graph G is a Euler if and only if degree of every vertex is even. A connected graph G has a Euler trail if and only if it has at most 2 odd vertices. Now come bridge problem. So this was the figure which you saw in the very first slide. This has been now redrawn as ABCD, where ABCD represents the region to reach, crossing the bridges. All the edges are the bridges. So now Euler gave the result that there is no such Eulerian cycle because a connected graph G is Euler if and only if only the degree of every vertex is even. You can see here there is no even degree vertex and so there is no such cycle formed. Hamiltonian graph. A Hamiltonian path in a graph G is a path which contains every vertex of G. A Hamiltonian cycle is a cycle which contains every vertex of G, and similarly a Hamiltonian graph is a graph in which there should be a Hamiltonian cycle in it. There is an example. This has an Hamiltonian cycle. I would B, E, C, D and come back to A. We are skipping one edge B and C in between and so we can form a Hamiltonian graph. The next are few results on Hamiltonian graph. If G is a simple graph with vertex n, where n is greater than or equal to 3 and the degree d of v is greater than or equal to Hamiltonian graph, let G be non-adjacent to each other, such that the sum of its degrees are greater than n, then G plus uv denotes a supergraph of G obtained by joining u plus v by an edge. Then G is Hamiltonian if and only if G plus uv is Hamiltonian. A maximal non-Hamiltonian graph. A graph G is called connecting two non-adjacent vertices. It forms a Hamiltonian graph. I have 15 vertices. It will create a Hamiltonian graph. The closure of a graph. Let G be a simple graph if there are two non-adjacent vertices u1 and v1, such that degree sum is greater than n. Then we join the edges to form a supergraph G1. We are continuing this process for another two set of vertices u2 and v2 and summing the degree as greater than n, then it gives the new supergraph G2. Continuing this for all the non-adjacent vertices in G, the final supergraph thus obtained is called closure of G and it is denoted by C of G. Example of a closure graph. This is a very first graph in which we can see u1 and v1 are not adjacent. As they are non-adjacent, the degrees are 3. If we add both the degrees, 3 plus 3 gives us 6, which is greater than or equal to the total number of vertices, and we are getting the graph. This G1 is a supergraph And you can observe that U2 and V2, and continuing this, the last graph, G7, it is a complete graph. And after this graph, we cannot have any non-adjacent vertices, and this forms a closure of the graph G. The next topic is a planar graph. A plane graph is a graph drawn on a plane in such a way that means it do not cross or intersect each other. A planar graph is in which isomorphic to a plane graph. What does this actually mean? I have this graph G1, but I say this is a planar. How? Because we redraw it, see that no edge intersects each other. So planar graph. Results, planar graph and the Euler's formula. A plane graph of graph. Euler's formula. Euler gave a formula that G is connected plane graph with N, E and F, which denotes number of vertices, number of edges and number of faces of G respectively. Then N minus E plus F is equal to 2. The corollary gives that let G be a plane graph with N vertices and faces, K connected components, then just where number of vertices are 5, edges are 8, faces are 5. However, there is one whole complement face, so it is total 5. The formula is N minus E plus F, which I substituted the values, and we get answer 2. So yes, our Euler's formula has been verified by this particular graph, and you can check that it can be verified by all the graphs. 5 vertices. K5 is a non-planar. A complete bipartite graph. K33 is non-planar. A graph is if n is greater than or equal to 3 and E is less than or equal to 3n minus 6. If G is a planar graph, then G has vertex V of degree less than 6. Few applications to hide the relationship among interconnected computers within the network follows the principle of graph theory. It is used to represent the network connection and also to find the shortest path of roads. In Google Nodes, and the roads are represented as edges and graph theory. It is used to find the shortest path between two nodes. This nodes here, which is connected by edges. Graph theory is also used in network theory of maps with 4 colors. Few more applications is in electrical engineering, linguistic. Graphs are mostly used for parsing of language. Trees and grammar of, for example, there is a theory of optimality which uses lattice graph. These are common in analysis of language as a graph. In physics and chemistry, graph theory is used to study molecules. Graph is also helpful in these are a very few examples which have been highlighted for this graph theory. We can have many such examples where we use graph theory. Everyone for being a nice audience. Thank you so much to everyone. Keyur sir, I hand over to you.
Yes, ma'am.
So any questions are there? Yes,
No, thank you
please.
so much, ma'am, for such an interesting and knowledge-sharing lecture. Now we are going to start the question answer session. If any participants have any question, they can type in the chat box. We will, ma'am, just wait for a minute. After that, we will conclude the session. If any participants have any questions.
Sure, sir, no problem.
Yes, ma'am. I think all are clear. Nobody has any doubt. So, on behalf of
Okay,
KS
sir.
School of Business Management, I thank Ms. Karisma K. Rawal for delivering such an informative talk. Thank you so much, ma'am.
Thank you so much, sir, for your kind words. Thank you.
Thank you, ma'am.
Okay, thank you, sir.